Hey everybody. So what I want to do over the next few days is give you a brief intro into integer programming. Okay, we're not going to dive super deep into it, but it is something that I wanted you to have seen in an intro LP class just to know kind of what's out there in the other fields of optimization. So just a brief touching, kind of like we did networks. I just wanted you to see some of the network stuff. I want to show you some of the integer stuff. If I have time, I'd like to show you a little bit of nonlinear optimization as well. So here's some integer programming, just a brief intro. Nothing super deep. So let's actually just start with an example, a problem. So let's say you own a small bakery and you'd like to maximize your profits. So your two biggest selling cakes are your famous 15-layer chocolate cake, I'll just call it LCC, and your strawberry pound cake. Okay. Now, as a small bakery, you have limited oven space. You only have so many ovens, and so you only have 50 hours of baking time each week. Well, the layered chocolate cake takes 2.5 hours of baking hours per cake, while the strawberry pound cake takes 1 hour and 15 minutes of baking time per cake. Okay. Now you also have limited number of employees. You're a small bakery. So that means that there's only so many work hours around to do stuff. So you only have 55 hours of non-baking time, like mixing ingredients, icing cakes, putting them out on the shop, all that kind of stuff. That's per week. So now the layered cake takes 1.8 hours of non-baking time per cake, while the strawberry one takes 1.75 hours of non-baking time. Okay. Now you have a 15 of those cakes. So the most we can make in a week is 15 cakes. Okay. Now the demand on the strawberry ones is limited. The most we ever want to make is 25. Demand doesn't seem to go over that, so we're kind of limited to 25. If we make more than that, we're probably just wasting ingredients. We may not sell them. Although if I own the bakery, I may just eat them all. So keep them away from me. Alright, so your profit per the layer one's $4 for each cake, and profit for each strawberry one's $3. How many of each cake should we make to maximize the profit? So this sounds like just a normal linear programming problem that we've done in this course. Everything sounds normal. We have our constraints. I made this problem up. I felt like eating cake, so that's why I wrote it. So how can we maximize profit? So the first thought is, okay, well let's model this like we normally would. And so I've gone through all the pains of modeling it. Let me not make this overwhelming showing you. So there's the profit. We want to maximize that, right? And then I wrote the oven time constraint. I only have 50 hours of oven time. The non-oven time constraint, fridge space constraint, and the demand limit. Okay. The side note, sorry, I can't help it. There's so many interesting things here. Whoa, didn't mean to do that. I wanted to turn the color back to gray. This is also called a bounded simplex, when our variables have bounds on both ends of them. And there's other techniques to solve these, but you can always just put extra bounds as constraints like these. So maybe if I have time, we'll see how many days we have left in class. I'll show you the bounded simplex as well, another way for handling these more efficiently. But we'll just introduce this as constraints for right now, okay? That works just fine and dandy. So let's say, there it is. So we can solve this in Python like I showed you on Friday. I actually have it typed in already. There's my code. There's the cost. Remember, you have to change it to minimization. And there's the A matrix and the right-hand sides. Control Enter. Boom. Let's see. So there's our maximal amount of profit we can make off those two cakes is $102. And then we get about 8.8 and about 22.4, 22.3, 22.4 as our optimal solution. So that's fine and dandy. Any issues with that? So go ahead, tell the chefs, I want you to make me 8.8 layered cakes and 22.3 strawberry cakes. Good, right? There's a problem. Do you really make a 0.3 of a cake? Most people don't. Now, some bakeries make half cakes, but let's just pretend we only make whole cakes. We only want whole cakes. I'm not going to try to rework the recipe. I'd have to refigure baking time. I'd have to do a lot of fancy stuff to figure out how to make 0.8 of a cake. So we want whole cakes. So this is where we need integer programming, because we want this to be an integer, not a decimal. So we need this integer programming. So any ideas of what to do to handle this? Any ideas? Well, there's a lot of ideas. Let's actually look at the graph to try to see kind of what we think about this. So here's the graph of the constraints. The optimal, the 8.822 is right there. Now, we're going to want it to be an integer, so how these often look is they're dotted with dots on every integer point. I don't know if I can draw that well, all these dots, where all the integers are. And what you end up finding is there will not be all the edges here will not all be integers. This is not, well, that one might. This is an integer, but not all these intersection points are guaranteed to be integer intersection points. So that's kind of the first thought here, is that, oh my, looking at this problem, our intersection points don't have to be integers. So some of these pieces of the graph may not be integers. So what happens is then the solution isn't going to be at one of these corner points then, because I can't have this corner point. It's not feasible. It's going to be something inside of there. So that kind of shakes up the normal simplex method and how we solve this stuff. So how can I fix this so that I could use the simplex? Well, first off, some people just say, well, let's just round. What could go wrong if we round, right? And so let's see, what did we get? We got about 8.8 and 22.3. We could just say, hey, what, 9 cakes and 22 of the other cakes. My first question is that even feasible? It might be. Rounding works some of the time. Is that an okay idea? Sometimes. Let's go back and check. Does 922 even feasible? Let's see. Oh, might need a calculator because these are kind of nasty constraints. So some people say, well, just round it down, but then you may be missing something. So anyways, is it even feasible? So another way to do it, idea number 2 is, okay, well, if rounding's not always the best idea, actually, there's some famous examples of rounding where people solve their integer programming problem, just round to the closest integer point, and then they end up being miles away from the optimal. I'm talking the optimal's over here somewhere. Because of the techniques used, usually on a 2-dimensional plot like this, rounding's going to be okay usually there. But it's when you're in more dimensions, something that you can't visualize, and you try to just round a few of them, you end up being very wrong sometimes. There's famous examples where some companies tried to optimize without hiring an OR person and just rounded because integer programming is hard. It's a hard problem compared to linear programming. And they said, oh, we'll just round. It's no big deal. But they've been far off. And when they did get an expert in there, they've saved millions or sometimes even billions of dollars. So rounding's okay. It works sometimes. That's what we do when you haven't taken integer programming. But sometimes it's very bad. So sometimes it's good. Sometimes it's very bad. Okay. So the next idea. Well, if it's the integer points, couldn't we just check all of these integer points systematically or combinatorially? Check every integer point. And you could even say, look, I know it's not 0, 0. I know it's not these. I could just check half these points. Maybe all these points up here. Is that a good idea? Well, there's a lot of points there. right? That's going to add a whole lot of complexity. If you're doing it on a computer, that's going to add a whole lot of computer runtime and eat up a whole lot of computer memory. It's going to cost you a lot as far as computing goes. So typically, that's not a good idea. Now, I will say, there are famous integer programming problems where pretty much most of the time the only way to solve them is to combinatorially go through all combinations. And so that's where a lot of integer programming is considered very hard. Not hard as in like, oh, it's hard to do, like, there's techniques, but hard as in like, this is going to be tedious. This is going to take you checking everything. This is going to cost a lot computationally. The method for doing this may be pretty convoluted. Okay, so I'm not going to teach you too much in depth here, but I want to show you two methods. So just today in this lesson, I'm going to show you one method that is used. So that's my third point here, is we might need another technique, and there's something called cutting planes. Okay, cutting planes. So I want to explain the idea to you, just so you know how integer programming works. There are two big techniques. Cutting planes is one that's interesting. One that's used a whole lot, I'll talk about in the next lesson for Friday's lesson, okay? That one's pretty interesting as well. So let's go look at the next slide. I have a smaller example where I listed out. So cutting planes, what's the main idea? So here's the main idea. It's this thing called a convex hull. A convex hull. That's a fancy phrase that means something. I'll tell you about this in a second after I explain cutting planes. But I'll go ahead and tell you pretty much convex hull. The idea of a convex hull is kind of the golden goose if you can get it. Okay, it's not always possible easily. And if you can come up with a convex hull, you are golden. Okay, you can solve it just like a linear programming problem, and you will be amazing, and you will be awesome, and you're good to go. That would make, as long as this doesn't cost you much to come up with, that would make all your problems solve in linear time or polynomial time. Well, we all know Simplex technically isn't polynomial, but it usually solves in 3M. It solves fast. It's simple, right? So let's just make up another problem simpler than the last, because my last problem I had fun creating, but it's pretty bold. Let's do a simpler problem so we could look at this and talk about what a convex hull is and what a cutting plane is. Okay, so say we're optimizing maximizing x1 plus x2, something really easy. And here's the feasibility region. I'm just going to show you the graph, not even anything else, the constraints. So there it is. This green line is my ISO profit line. We're maximizing, so it's pushing that way. The green line's pushing that way. So pushing up looks like right here, if we solved it as a linear programming problem, would be the optimal. Notice that is not an integer. Do you see that? That is not the integer. Okay. So that means that this is the optimal of the LP, but it's not the optimal for the integer programming problem. Okay, because it's got to be an integer. So all these red circles are the integers that are inside feasibility, the feasible points. All right, so it's got to be one of these. So you don't want to have to check all of them. That would take a long time. So you may just round. So I actually, let's see, put this in Python and I ran it. And here's what I came up with. The solution was 5.5. That's that same point, right? But I just wanted to get it 5.5 and 3.75. 5.5 and 3.75. And I think I wrote that down. Yeah, 5.5. So that's infeasible, though. So we could just round, right? Round to the closest point, which would probably be this one, right? Round to the closest point, which would be, had to round that down to 5, and that would be up to 4. 5, 4. In our objective function, I made it simple so we could find the max. So that'd be 9. I'll go ahead and tell you rounding works. Rounding usually works when you're on something simple like 2 dimensions. But how would you do this if I'd said no rounding allowed, find the optimal? Well, here I want to show you all the close points. I checked all of these points along in here. N54 is the highest objective function value. Check the rest. There's a bunch of them that have 8, and then some that have 7, and some that have 6, and there's more in here that have similar values. Okay? But, so, like I wanted to make a big point here. It appears that rounding would work. That gives us the optimal. This is not always the case. I put it in all caps. Not always the case, because that's usually sometimes a very bad idea, and we never want to assume things in math. So let's talk here. Last little bit of this video is, so what is the basic idea behind cutting planes? Well, it's all this idea of a convex hull. Okay? So what the convex hull is, so let me draw it over here. So let's say you have some constraints, and say this is how they look. Okay? And the green dots are integer points. Okay? So these are the feasible points. And these are the only feasible points. Okay? So here's the idea of a convex hull. I'm going to draw it in red. It's like if you could take a rubber band and put it around the outside of this and get it tight on all the way around and make a convex, not concave, it has to be convex, a convex polygon around it. It's got to be convex. That would be our convex hull. Oh, I guess it has convex in the name, sorry. So that would be the convex hull in red. It's when we come up with all the equations. This one's not straight. We could, if we have the convex hull, then here's what I'm guaranteed. I can solve this new constrained area as an LP, and I would get one of the corner points like I always do, and that would be the optimal solution. So if I could create the convex hull, it would solve like an LP. Okay, I could just do the simplex method and say, oh, boom, there's the optimal, or boom, there's the optimal. One of the corner points would be optimal. So how do we come up with the convex hull? So let's go back over here to this example and talk about, that's where the idea of a cutting plane comes in. So let me erase some of my writing here. So we would sit and look and say, okay, here is what we got. We got this right here. This is optimal for the linear programming problem, but it's not optimal for the integer programming problems because this point is not feasible. So we'd like to, or we need to cut off. Need to cut off. So in some dimensions, like in 3 dimensions, we'd cut this off with a plane. Okay, in this dimension, it's just a line, but we're going to come up with the equation of some line that would cut off this point. Now, typically, when people do that, they want to try to pick wisely and intelligently. So they might try to get it to go through. Too bad, I should have had this angled, because then you could see me add a cut. So we'd like to come up with a line that cuts through. It could even be, and this is where it gets pretty difficult. It could be any line that cuts off that point. So technically, you could come up with good cutting plane cuts or feasible cutting plane cuts that don't really help you a whole bunch. There's infinitely many kind of that could go through here, right? But there are things that are the best, or maybe not the best, but pretty good cutting plane cuts when you cut through more points. Okay, and you try to create a convex hull. So for instance, I could add a constraint. Okay, I could add a constraint, and what it does is it makes this constraint redundant. I don't even need this constraint anymore. But I can add the constraint that we got to be less than, x1's got to be less than 5. So now I've cut off this slack space here where there's no feasible points anyways, right? And then you solve again. And if you happen to pick up the optimal, yeah, you're good. If you don't pick up the optimal, say I got this point right here, well, then I need to cut off this point. So I'd come up with the equation. The best equation here would be one that cuts it off and goes through these 2 points. And so now look at what I'm getting. I'm getting what looks like the convex hull. Now understand, this is extremely difficult in more dimensions, especially really, really high dimensions. And you may have to add a whole lot of cuts before you cut it down to where you can find the optimal. You may add one cut and find the optimal. But you may have to add a whole lot of cuts before you even get close to a convex hull. This one looks like it takes 2, and I've created the convex hull right there. Boom, boom, boom. So that's the idea behind cutting planes. Is the main idea is you are adding constraints to cut off, and I'll put that in quotes, cut off non-integer extreme points. Extreme points. Okay, and I'll go ahead and once again just reiterate, and then I'll be done. The goal is, if you can create a convex hull, then I could just save this. Not save it, solve it as an LP. The goal is to cut off as much of this non-integer points as long as you're not cutting off any feasible. Notice I did not cut off any feasible points. They're all still inside the constraints here. And so that's the goal. You cut off non-feasible points to try to create something that can solve as a linear problem. Okay? All right, so I'm going to leave you there. Next time we're going to look at, I'm going to introduce some famous integer programming problems and then show you how those are best solved. Okay? Well, maybe not best solved. Some of them are pretty challenging to solve in anything that's even close to polynomial time. But anyways, y'all have an awesome day, awesome night whenever you're listening to this, and I will see y'all on Friday.